Uh-oh. Sorry. Okay. All right. So we'll go ahead and get started. So it's week 3, and we are ticking away. So what we are so this week we have a midterm exam on Friday, and that's not our normal class time. We normally meet only on Mondays and Wednesdays. But I asked, is this kind of thing allowed to kind of schedule exams outside regular class time, and it's an allowed thing, and that allows me to have a review session on Wednesday, which I think will be helpful in allowing kind of the material I covered today to kind of just have a little bit of time to settle in and for you to get some practice. So anyway, regarding the exam on Friday. You can choose to take the exam either from 10 a.m. to noon on Friday, July 10th, or from 10 p.m. to midnight on July 10th. And those are that's California time, and so wherever you are in the world, at least one of those times should be during daytime or something, because I know for some people this class as it's held right now is like 3 in the morning or something, and that's not a great time to be taking an exam. So anyway, you don't have to tell me which session you're going to attend. Just show up and take the exam. The exams will be proctored via Zoom. Okay, so you'll just log in, you'll turn your cameras on, you'll stay muted, and I'll just kind of monitor the Zoom screen. If you'd rather, you're able to, you can choose to install Zoom on your phone or tablet and log into Zoom that way instead of your computer if you want. You can use your computer. It doesn't really matter to me, but that's how I'm going to proctor it. So I'm not going to use Respondus or anything like that where it's recording stuff, but just I'll be monitoring that way. The exam is going to be completely multiple choice and will be taken on CCLE. I'm still writing the exam and and working on questions there. So hopefully by Wednesday when we do the review session, I'll have a better idea. I probably won't actually finish the exam writing itself until Thursday, just because I'm always making tweaks and stuff. But that's the plan. The exam is going to be open note and open book, and students are allowed to use a calculator of any kind. You're also allowed to use RStudio for calculations if desired. So if a problem asks you to find the standard deviation, you can choose to do it by pen and paper. You can choose to use a calculator. You can choose to type it into RStudio. So that's fine, yeah. And kind of the one rule that I'm going to be strict about is you are not allowed to talk to each other or communicate with each other about the exam, okay? And so I guess I'll remind you, but if you take the exam at 10 a.m., after you finish at 10 a.m., don't talk about the exam, especially because there's going to be students who will take it at 10 p.m. later that day. And then also, even after you take it at 10 p.m., please don't talk about the exam. I anticipate there will be a couple students who need makeup exams, and so I don't want them getting an unfair advantage about knowing what content is going to be on the exam. So I'll set a reminder just to say don't talk about the exam. Okay, I got a few questions here. One asked, is there no quiz this week? There's no quiz this week. You have an exam. And can I make the slides visible? Yeah, I can upload. These are draft slides. Okay, slides draft. Okay, so so the draft versions of the slides are up. Okay, and then question says, will the exam cover all material we have gone so far, including what we'll cover this week? Yes, so the exam will cover basically chapters 1 through 6 in the textbook. Basically, all of the lectures that we've gone over so far, including today's lecture. And that's why I'm choosing to put the exam on Friday rather than Wednesday, to kind of give it a little bit more time to settle in. It's, you know, we're trying to compress an entire quarter's worth of material in 6 weeks, and so you know, it feels like the class just started, but you know, it's already time for an exam. So so what I'm going to do is hold a review session on Wednesday, okay, and that'll be during our regular class time from 11 to 12:50, and I'll record that. It's optional. There's not going to be a viewing quiz or anything like that for the review session. Just come and do some practice problems and things like that. So I'll go over a little bit more detail about kind of the content of the exam, but I mean the short of it is it's chapters 1 through 6, and yeah, and we'll do some practice problems there. So so that will be Wednesday, and that's that. Okay, and then I normally have office hours on Fridays at 11, but it doesn't make sense to have office hours during the exam. So I'm going to move my office hours to Thursday at 11, okay? And so, you know, if you have any kind of last minute questions, or, you know, questions, you know, the day before the exam as you're studying and whatnot, you can join me on Thursday with your questions and things like that, okay? Are there any questions regarding kind of just the logistics of this week? Okay, so no one has asked this question, but it's a question that pops up. Is you know, is lab content going to be covered on the exam? And so the answer is it is not going to be directly covered. Okay, but that said, is that, you know, you are allowed to use R as kind of a tool to help you answer questions, and so in that regard, being familiar with R could be helpful. I will say you should be able to answer all of the questions without R. You can, if you are kind of comfortable with a calculator, like a scientific calculator, you should be able to answer all of your questions. But the questions could be aided or made easier with the usage of R. Okay, and that's an option that's open to all students who want to try to use that for a handful of questions. So I would say, you know, and I'll go over the content, but there will be a good mix of, you know, questions that require calculations and questions that are a little bit more definition and conceptual. So so in that regard, the exam, I won't ask, you know, direct questions about R, but the questions could be assisted in answering by that. Can you submit late quizzes? That's a question. Okay, so when you start a quiz, it starts a 60-minute timer. Maybe, I think maybe 63 minutes or 64 minutes or something. It starts a timer, and you absolutely must submit the quiz by the end of that deadline. Otherwise, GradeScope locks up. So that's that's that. Yeah, I guess if you have further questions, you can email me directly. I think you might have actually, this is a private question. You might have emailed me already. I just need to get around to responding there. Do we have an exam Zoom link? Just use the lecture Zoom link. Okay, so for the exam, use the the Zoom link that you use for this, and that's where we'll be. Okay. I do have a different link for office hours, and that's because the office hours room is set up a little bit differently in case I need to have like a private conversation with a student if a student's having a wants to have a private conversation. So that's why my office hours link is different. But for the exam, just use the link that you're using today, right now. All right. Well, I guess we'll go ahead and get started on today's lecture. And today we're going to cover Chapter 6, which is about probability distributions. And so, kind of the big picture idea that you know, I always try to tie each of my lectures back into the big picture is that in statistics, we want to make conclusions from data. And in order for us to do that is we've got to be able to distinguish between actual phenomena, things that are actually happening, and things that are the result of random coincidence, okay? And so to be able to understand what could the difference between something, quote, like actual phenomena versus random coincidence is that we've got to understand what random coincidence could look like. What could randomness look like? And in order to do that, we have to learn probability. And so we started kind of learning a little bit about probability last week in Chapter 5. And today we're going to kind of expand on that, go from kind of the basic rules of probability, and we're going to get into what's known as a probability distribution. We'll start that off with what we call the binomial distribution, and then we'll get into the normal distribution. And probability distributions, we'll talk about those, but you know, they're kind of tables or a way to describe probabilities of outcomes here. All right, and I think I showed this example last week as well, and so here's kind of an example of is there an actual phenomena or is this random coincidence? So so for example, you know, let's say you've got this carnival game where you spin the wheel, okay, and there's like 12 spaces on the wheel, and half of the spots are marked, you know, you lose money, okay, or you just don't win anything, you lose, and then the other half correspond to some kind of prize, okay, and so, you know, maybe most of them are like small prizes, and maybe one of them is a big prize or something like that. So anyway, you should win about half the time you play, right? If half of the spaces are winning and half of the spaces are losing, you should win about half the time. And your friend plays, after your friend plays 10 times, he comes back and says, I think the game is a scam because I only won 3 times, right? And so now the question is there actual phenomena in that is the game a scam versus is it just random coincidence? Did our friend just get unlucky, right? Because if the game is truly fair, when our friend plays 10 times, we expect he would win around 5 times out of 10, right? If half of the spots are wins, if he plays 10 times, we're expecting him to get around 5 wins. But he only won 3 times, okay? And that's less than 5. So does that mean the designers of the game have made the game to be a scam, okay? Or is this possible, right? Could the game actually be fair, and by random chance, random coincidence, our friend just got a little unlucky, only won 3 times out of 10 or something like that, okay? So this is kind of the question that we want to be able to answer in order to use statistics and probability to differentiate between actual phenomena and random coincidence. And so, so today we'll learn how to calculate the probability of this outcome of, you know, kind of winning only 3 times out of 10. So, so that's kind of where we're headed today. And actually, we'll tick it off when we talk about the binomial distribution. But that's kind of the overall theme for the future of our course. So after the midterm, so prior to the midterm, you know, the first 3 weeks we covered chapters 1 through 6. It's kind of like a whirlwind here. And then after the midterm, my goal is to cover chapters 7, 8, and 9. And I only have 3 chapters planned, but they're a lot heavier. They're a lot more, the content is a lot more substantive, I don't know. And that's typically what we would cover in a full 10-week class. We would cover maybe the first 9 chapters of the textbook. But anyway, today's chapter, chapter 6, we'll just talk about kind of what a probability distribution is in the first place, and then we'll build on that and talk about the binomial distribution and the normal distribution. And these are kind of the key topics for today. I guess before I go on, I just want to kind of make sure that the setup that I have in terms of I don't know, is this carnival game, does that feel like a scam? Does that make sense to you guys? Is everybody feeling okay about that? Kind of just the idea of distinguishing between an actual phenomena and random coincidence. Okay. All right. Yeah. Thank you. Thank you for your green check marks saying yes. I'll go ahead and give you your first quiz answer for today. So today's first quiz answer, week 3, Monday, is E. E as in elephant. That's our first quiz answer. E as in elephant for our first quiz answer. Okay, and again, Wednesday's review session is optional. There's no viewing quiz there. So okay, so a probability distribution, what it does at the heart of it is it describes the probabilities that a random variable can take, the random variable, okay? All right, so what is a random variable? A random variable is the numeric outcome of a random trial, all right? So there's a couple pieces there. It's got to be numeric, and there's got to be a random trial, right? So it's kind of like you have random trials, okay, whatever it might be, flipping a coin, rolling a die, drawing a card, picking a person at random, doing, you know, reaching into the hat and grabbing something. You do something random, okay? And this thing that we're doing, this random trial, has to be set up in such a way that the outcome that we're going to write down, the outcome that we're recording, it has to be a number, okay? So if we're talking about flipping a coin and it landing heads or tails, we can't write heads or tails. That's not going to count as a random variable. For it to be a random variable, the outcome has to be a number, all right? And we might see that certain outcomes might be more likely than others. So, you know, with flipping a coin, heads and tails are equally likely. But maybe you have a special coin, a weighted coin, where one side is more likely than the other or something, okay? And the probability distribution, what that does is it shows the probabilities associated with the different possible outcomes, okay? And we can represent these probability distributions with a table or with a graph. And so I'm going to just show you just a few examples to kind of give us, I guess, familiar with probability distributions, and then we'll kind of go from there. So, so here's a simple trial. Wait, let me grab my giant die. Okay, and so here I've got, you know, if I roll a die, it can land on any one of these faces, right? So it can land on the 1 or the 2 or the 3, you know, any one of these faces, they are equally likely. And so the random variable can just be the number that lands face up when you roll the die. And that's simple, right? Because for it to be a random variable, the outcome has to be numeric. So the random variable can just be the number of dots that show up on top. Okay, and each of these sides are equally likely, and so this is my probability distribution. The outcomes that are possible, I list them off as x for my random variable are 1, 2, 3, 4, 5, 6. And here we write probability that x equals x, meaning the probability that this random variable x takes on the value 1 or 2 or 3 is equal to 1/6. 1/6, it takes on the value 1 with probability 1/6. It takes on the value 2 with probability 1/6, so on and so forth. That's rolling a die. And if I plotted this, okay, the x values can take on 1, 2, 3, 4, 5, 6, and the probability distribution looks like, I don't know, looks like a little ruler here, but each of these lines has a height of 1/6. 1/6 is around 0.1667, and there's 6 lines, and they all have the same height. So all 6 of these lines have the same height there. So that's rolling a die. Okay. I've got another example here. One is our random trial is a coin flip. Can I go back briefly? Sure. Did you have a question? So don't worry too much about the the commands I've used here, but basically x can take on the values 1/6, and the probabilities associated with them is 1/6 for each of these, and so they're all the same height. All right, so when we flip a coin, okay, the coin can land heads or tails, okay? And again, for it to be a random variable, the outcome has to be numeric. So we can't just say, hey, write down whether you got heads or tails. That's not going to work for a random variable, okay? So it feels a little silly, but you can just answer it with, okay, well, you flip a coin once, how many times did it land heads? Okay, how many heads, a random variable, can be how many heads appear after one coin flip, right? So if the coin lands tails, then the random variable is equal to 0, right? If it landed tails, it landed heads 0 times. And then if it lands heads, the random variable will take on the value 1, right? So just by kind of changing it from did it land heads or tails, if we just say, hey, let's count how many times it landed heads, now we have a random variable because the outcome is numeric, okay? And so we're going to get 0 with probability 0.5. We're going to get 1 with probability 0.5, right? And so this is a random variable that it's got to be a numeric outcome. So we're not going to just write heads or tails. We're going to make it numeric somehow, okay? And this this is what the graph would look like for the coin flip, and it's not very exciting at all. We've got 2 lines, one at 0 with a height of 0.5, and a line at 1 with a height of 0.5, okay? Okay, so this one we have to apply a little bit of our probability rules, okay? And what we're going to do is we are going to flip a coin 2 times, okay? We flip a coin twice. And when you flip a coin twice, these are the possible outcomes. We can get heads, 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 tails, tails, heads, or tails, tails, okay? And again, we can't use this as a random variable because it's not a numeric outcome. So we have to somehow convert this into a numeric outcome. And you know what, there's not going to be a way for us to really do like a one-to-one outcome. Okay, we're not going to be able to say, all right, this one's 0 and this one's 1 and 2 and 3 or something like that. There's not going to be a one-to-one, but we can get something that a random variable associated with 2 coin flips, and that would be how many heads appeared after 2 coin flips. Okay, how many heads appeared after 2 coin flips. And so the outcomes when you do 2 coin flips is that you can get 0 heads, you can get heads 1 time, or you can get heads 2 times. And that covers all possible outcomes. When you flip a coin twice, how many times can heads appear? It's either going to be 0, 1, or 2. There's no other possibility. Okay. All right. And so here I'm using the probability rule for probabilities of sequences of independent events. I hope you guys remember that from last week. And so the probability of getting 0 heads is going to be 1/4, because we need to get tails, tails, and that's going to be the probability of tails times the probability of tails. So 0.5 times 0.5, and the probability of getting tails, tails is 0.25. Okay, so that is this. Okay, x equals 0 with probability 1/4. All right. With 2 coin flips, we can get 1 head, and that's going to have probability of 1/2, right? And so there's 2 possible ways. We can get 1 head with heads, tails, or with tails, heads. Okay, and the probability of heads, tails will be probability of heads times the probability of tails. And then the probability of tails, heads is going to be probability of tails times the probability of heads. So this has a probability of 0.5 times 0.5. The other one has a probability of 0.5 times 0.5. So this is 1/4, this is 1/4, and you add those together and you get 1/2. Okay, and then similarly, probability of heads, heads, you multiply 0.5 times 0.5 and you get 0.25. So this is all the possible outcomes. 1/4, 1/2, 1/4 are their associated probabilities. So you get x is 0 with this probability, x is 1 with this probability, x is 2 with this probability. All right. Okay. Are we good with all of this? Do we feel okay? Again, if we're feeling good with all of this probability stuff, probability distribution so far, give me a green yes. If you got questions, you need me to go back, say no, or throw your message in the chat there. Okay. And again, the first question today, first question for the quiz was E as in elephant. That's a repeat of the first question. Okay. Okay, and then so if I plot that, this is what the graph looks like. 0 with probability 0.25, 1 with probability 0.5, and 2 with probability 0.25. Okay, and so we have this outcome. All right, and then another one more of these. Okay, so we talked about kind of spinning that game wheel at the carnival. All right, and so if this was a fair game and all 12 spaces are equally likely, all right, maybe we have 6 of them marked to be lose, 5 are small prize, and 1 is labeled, one of the spots is labeled big prize. Okay, and again, we can't use the outcomes lose, small prize, or big prize because they are not numeric, right? For it to be a random variable, the outcome's got to be a number. And so, you know, what we can choose will be the dollar value of the outcome, right? We could say, how much is losing worth in dollars? How much is the small prize worth in dollars? How much is the big prize worth in dollars? So we can say lose has a dollar value of $0, okay? Small prize maybe is worth $1.50, okay, $1.5. And big prize maybe, I don't know, you get a big stuffed animal and maybe that's worth $6, right? I'm just thinking of, like, I don't know, you go to the fair or something and they get, like, you know, you throw the ball to knock down the cans of milk or something. All right, and so if you do it, you get, so this is a, yeah, so 0 takes on the probability of 1/2 because 6 out of the 12 are marked lose. And then the small prize, which has an outcome of 1.5, has probability of 5/12. And then big prize has a value of 6, and it has a probability of 1/12. Okay. And so the graph for that might look like this. So we got 0 goes up to 0.5. 1.5 goes up to the probability of 5/12. 5/12 is something like 41% or something. 41.67%. All right, and then it takes on the value of 6 with probability 1/12, and so this bar has a height of 0.083. Okay, so so this is our probability distribution here. Okay, so all of these so far are what we call discrete random variables. Okay, a discrete random variable means you are able to list off in a table. You can say the value can come out to this number, the value can come out to this number, the value can come out to this number, and you're able to write down a list of basically the different possible values, right? If you're able to kind of list them out, then the random variable is discrete. Okay. On the other hand, random variables, there are other random variables that we call them continuous random variables. They can take on decimal values. Okay. So for example, we can say, you know, you grab a handful of sand and you weigh it. Okay. How much does that sand weigh? All right. And I don't know how much a handful of sand weighs, but maybe it weighs like 24.67 grams. Okay. Someone else could grab a handful of sand and they might get 24.6634 grams. Okay. And technically, if we had a very, very, very accurate scale, the number of grams, you know, the number of decimals could go off into infinity, right? And we would not be able to list off every single possible outcome. And therefore, that's a continuous probability distribution, okay? So, you know, when you have a discrete one, you can make a table, okay? Or you can make the graph with the lines, okay? If you have a continuous random variable, you cannot make a table, okay? There's not going to be a table because you're not able to list off all the numbers, right? If I say write down all the numbers between 0 and 1, you can't do it. You wouldn't even, like, what's the first number you're going to write? You can't, right? Because what's the smallest non-zero value possible, and you can't even write that, right? It's like so you can't make a table of outcomes when you have a continuous random variable. So the way we represent continuous random variables is we can have like a curve, a line, maybe a line or a curve or something. You can do a graph, okay? If you study statistics, okay, it can also be represented with a mathematical equation, and we call that a density curve or density function. In our class, we're not going to worry about the mathematical equations, okay? That's for the stats majors and the math majors, but not this class, okay? So so we're not going to deal with the math equations, but we will talk about kind of the graphs and the curves here, okay? For continuous cases. So so here's just kind of to contrast, right? So if we select a random person, maybe the random variable that we record is going to be how many siblings does this person have, right? How many siblings? We can list those off, right? The person can have 0, 1, 2, 3, 4 siblings, 5 siblings, okay? And you know, we'll stop at some arbitrarily large number. I don't know what the world record is for the most number of siblings. I think the world record for one mother giving birth, I think she had 69 children, which is rather incredible. But okay, so maybe the world record for the number of siblings is 68. She had a lot of them were multiple births. I think there was something where she just, she gave birth to like twins and triplets multiple times. So just kind of a genetic predisposition for that. But yes, I think that's the world record for, I don't know, you look that up. I think anyway, it doesn't matter. Okay, so that would be discrete. You can write out all of the possible numbers that this can be for the number of siblings a person has, right? Okay, here's another random variable. Okay, and the random part is we're selecting a person at random. We select a person at random, and then the number, the numeric outcome that we're going to record is the person's height in centimeters. We say, how tall is this person? Okay, and that height can be something like 180.0. It could be 180.01. Okay, or if you had some really very precise measurement device, it could be 180.0127. Okay, and at that point, someone's height might change just from the fact that they're sitting and vertically or standing vertically, and the weight of gravity is slightly compressing their whatever, the discs in their vertebrae and things like that. And apparently when you sleep, your back decompresses, and when you wake up, you're a little bit taller than you are at the end of the day. And astronauts, when they come back to Earth after living in weightlessness, they are taller because their back has decompressed. But anyway, this is going to be a continuous thing. Okay, infinitely many values that are possible for someone's weight. Okay, and we're only limited by the precision of measurement, and so this variable is continuous. Okay, so here's just a simple example of a continuous random variable. We can say at a bus stop, it comes every 12 minutes. Okay, which is nice. I think the Big Blue bus in Santa Monica runs fairly frequently. I'm a big fan of public transit, but after coronavirus, I haven't avoided taking the bus, which makes me a little sad. But anyway, so let's say a person arrives at the bus stop at a random time, okay? And how long is this person going to have to wait for the next bus, okay? So technically, the person can wait anywhere between 0 and 12 minutes, right? They could arrive just as the bus arrives there, so they had no wait time. They could also arrive just as the bus is leaving, so they have to wait for the next bus to arrive. They have to wait 12 minutes for the next bus, okay? And they can arrive anywhere in between. So they might have to wait 1 minute. They might have to wait 1.5 minutes. They might have to wait 1.526 minutes or something like that, okay? And technically, all of the values between 0 and 12 have equal probability. And to show that all the values from 0 to 12 have equal probability, we're going to be represented by a flat line. And so this is what a continuous probability distribution might look like, okay? The probability of waiting less than 0 minutes is 0. The probability of waiting between 0 and 12 minutes is given by this line to show equal probability or equal density, technically. And then the probability of waiting longer than 12 minutes is going to be 0. Okay, and so this is going to be a line or a curve. We guess we might call it a curve to represent how long somebody would have to wait. Okay, so this would be a continuous random variable. All right, and the key here, why is it at 0.08? Okay, yeah, it's technically at 0.083, and and part of the answer to that is that the area must equal 1. So the what number times 12 is equal to 1? So if you do 1 divided by 12, you're going to get 0.083. That's a good observation there, and that's so that if I calculate the area underneath this line, the total area is going to be 1. That's kind of a rule regarding probability distributions. Okay, so if it's discrete, the probabilities have to add up to 1. So if we have a table, these probabilities, if we add them up, will add up to 1. Okay, all of these tables, the probabilities add up to 1. So if it's discrete, the probabilities have to add up to 1. The probabilities all have to be positive. You're not allowed to have a negative probability. Okay. If it's continuous, okay, again, you don't have individual values to add up. So what we say is that the area under the curve must equal 1. Okay, if you've taken calculus, this is equivalent to saying that the integral of the curve, the integral of the mathematical function is equal to 1. If you didn't take calculus and that didn't make any sense, don't worry about it. That we're not gonna worry about that, okay? But it is true, this part you do need to be okay with, and that's the total area under the curve has to equal 1. And so because it goes from 0 to 12, the height has to be 0.0833 because that times 12 is going to equal a area of 1. And that's that kind of goes along with the idea that the probability of kind of all of the possible outcomes is going to be 1. So, and then kind of going along with probabilities must always be positive, that line is never allowed to kind of dip below 0. Okay. So if it's discrete, the probabilities add up to 1. If it's continuous and you have like a curve or line, the area is equal to 1. All right, so let's expand on this and get into the binomial distribution, okay? So the binomial distribution is a probability distribution for a random variable. And these are the conditions that make it a binomial distribution, okay? We're going to repeat the same random trial n times. So like we flip a coin 5 times. We draw, I don't know, marbles out of a bag with replacement, 20 times or something, okay? We do the same random trial, we do it n times. And every time you do a random trial, there's only 2 possible outcomes. And that's kind of the bi part in the binomial, is that either something happens or it doesn't, okay? Traditionally, these are labeled success and failure, okay? And we generally, in English, we associate success with a good thing and failure with a bad thing. But these are just kind of arbitrary labels. They don't necessarily, like, we can say heads is success and tails is failure, but that, it's not like we're celebrating when we get heads. It's just something happened or it didn't, okay? Each trial is independent of the other trials. The outcome of one trial has nothing to do with the outcome of the other trial. And kind of going along with that is that every time you do the same trial, you're going to have the same probability of success, okay? And then, and the random variable that we're recording, the random variable x, is the number of successes. Okay, I think it'll make more sense if we do a slightly more concrete example, right? All right, so imagine we've got a special coin, okay? And I think we had similar examples back in last week. Okay, we have a special coin, and let's say the probability that it lands heads is 0.7. So we're gonna say probability of success is 0.7, which means the probability that it doesn't land heads is 0.31 minus 0.7. And what we're going to do is we're going to flip the coin 4 times. Coin flips are always independent, so the probability is always going to stay 0.7. And so the question is, what is the probability that we get heads exactly 1 time? Okay, so I'm going to start answering this question using the classical probability rules that we learned last week. Okay, and then I'll do this a couple times, and then we'll kind of try to identify a pattern to use the binomial distribution. Okay. All right, and so using the classical probability rules, what we do is we're going to list off the possible sequences where we get heads exactly 1 time in 4 flips, and these are the outcomes. Heads, tails, 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 heads, tails, tails, so on and so forth. There are 4 possible ways to get 1 head and 3 tails in 4 flips. And so if you calculate the probability of this sequence, or the probability of this sequence, or the probability of this sequence, each of those will have the probability of 0.7, because the probability of heads is 0.7, times 0.3 to the third, because the probability of tails is 0.3, and it has to happen 3 times, right? So the probability of the sequence of independent events is you just kind of multiply all of these independent probabilities together. So you do 0.7 times 0.3 times 0.3 times 0.3, and you're going to get 0.7 times 0.3 to the third, okay? And if we did that for any of these, we're going to get the same answer of 0.7 times 0.3 to the third, and that's going to add up, multiply out to 0.0189, okay? And if we have 4 possible arrangements, then the total probability of this, or this, or this, or this, we would add all of those together, because they're all kind of, they're mutually exclusive, so we can add them all together. So we would have, with 4 arrangements, we would have 4 times 0.07 times 0.03 to the third. And that gives me a total probability of 0.0756, okay? So let me pause there and just make sure this is okay with you guys. If you're following along and you're okay with this calculation, give me a green check in the participants panel. And if this is no good for you, please throw your question in the chat, or give me a red X or something here, okay? I just, this is going to be important as we go forward from here. Okay, all right, well, thank you to those of you who have responded. Okay, so this is how we solve this probability using kind of the classical rules, okay? Let me just do the same problem, except this time we're going to ask, what's the probability of getting 2 heads out of 4 flips, okay? 2 heads out of 4 flips. So same idea as before, we're going to list off all the possible sequences, and so there are 6 possible arrangements to have 2 heads out of 4 flips, and I've listed them off here. You can verify yourself. And if you calculate what's the probability of this sequence, or what's the probability of this sequence, or what's the probability of this sequence, okay? Again, you know, multiplication is commutative, so we're going to get 0.7 squared, because I've got heads times the probability of heads, okay? 0.7 times 0.7, and the probability of tails times the probability of tails is going to be 0.3 squared, right? So we got 0.7 squared times 0.3 squared. The probability of any one of these sequences is going to be 0.0441 if I do 0.7 squared times 0.3 squared. Okay, and again, I have 6 possible arrangements. All right, and so the total probability of getting heads exactly 2 times out of 4, 6 possible arrangements, is going to be 0.2646. All right, so so that's what we have there, okay? And so, you know, just with these kind of 2 examples here, I want to try to establish a pattern, okay? And so for the first example, when we said we're going to get 1 head in 4 flips, we said the probability of one of those sequences was 0.7 times 0.3 raised to the third, okay? And technically I can do 0.7 raised to the 1 power to kind of establish this pattern, because raising something to the 1 power doesn't affect it. And so this is equal to the probability of a success, which is 0.7, raised to the number of successes, which is 1. Okay, I needed, how many heads, what's the probability of getting heads was 0.7. How many heads do I need? It needed to happen 1 time. Okay, and we have a total of 4 flips. So that means we had to get tails, which in this case would be the fail. The tails is, has a probability of 0.3, and it had to happen 3 times, okay? So the probability of each one of those sequences was 0.7 to the 1 times 0.3 to the third. And because there were 4 possible arrangements, the total probability was 4 times 0.7 to the 1 times 0.3 to the third. Okay, and so that's going to be number of arrangements times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. Okay, the same pattern holds when we did 4 flips and we wanted 2 heads. Okay, it's still probability of success 0.7. This time we wanted 2 heads, and probability of tails, which is 0.3, the failure, and we needed that to happen 2 times, right? Because we have a total of 4 flips. We need 2 heads and 2 tails. The order doesn't matter, okay? But it's going to be 0.7 squared times 0.3 squared. That's the probability of any one of those sequences, whether it's heads, tails, tails, heads, or heads, heads, tails, tails, or tails, heads, tails, heads. It didn't matter. Any one of those arrangements had this probability. And we said, well, there's 6 possible arrangements. And so the total probability of all of that is the same. Number of arrangements times the probability of success to the number of successes times the probability of failures raised to the number of failures. And so let me talk about this value here, the number of arrangements, right? So what we did was we listed them off. I said there are 4 flips. How many ways can we get 1 head? And I listed them all out. I said, there's 4 flips and we're going to get 2 heads, and I listed them out. Okay, but that's going to get that's not a efficient way to do it. If I said, we're going to flip the coin 10 times, and how many ways can we get 4 heads? Okay, 4 heads out of 10 flips, you got heads, 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 tails, 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 and then there's all sorts of different possible arrangements. We don't want to have to go down the path of listing them all out. Okay, and let me just finish this one section, and then we'll take a break. I'll give you your second quiz answer shortly also. Okay. So rather than having to list off all the arrangements, we can use something called the binomial coefficient. Okay. This n over k inside parentheses, this is read as n choose k, right? N choose k, and we can and it can be calculated using n factorial divided by k factorial times n minus k factorial. Okay, I don't know if you've seen the factorial symbol, but it basically means you multiply all the numbers that are equal to or less than or equal to that number. So 4 factorial is 4 times 3 times 2 times 1. It equals 24. Okay, so 4 times 3 times 2 times 1, that would be 4 factorial. And that's what this is. And so, I mean, you don't, okay, again, open note, open book, you don't have to memorize all of this stuff, but here's just an example. If we did 4 choose 2, 4 choose 2 is 4 factorial divided by 2 factorial divided by 2 factorial, and that gives me 6. We can say, how many ways are there to get 2 heads out of 4 flips? The answer there is 6. If we have 10 trials and we want to say how many ways can we get 4 successes, we could do 10 choose 4, okay? And that would be 10 factorial, which is 10 times 9 times 8 times 7, all the way down to 1, which is this big number, 3,628,800. And then we divide by 4 factorial divided by 10 minus 4, which is 6 factorial, okay? All right, and so this is a bit of a mess. We don't really actually want to do this. So your calculator might have an NCR button. You can also use R to answer it, okay? So if you have a, I'll show you what my calculator, I have a calculator and it looks like, It looks like this. Your calculator might be different. You might have to hit like a PRB button to get it. On mine, I can do 10, and then there's an NCR over the division key. So I hit Shift, divide, 10, choose 4, and if I hit Enter, it's going to tell me it's 210. Okay, so that's 10, choose 4, and I got that by doing Shift, divide, NCR. If you have a Texas Instruments, you might have to hit the PRB or the math button to find an NCR command. So that's a possibility that you can have 10, choose 4. Okay, and you can go on to R and you can just do choose 10, 4, and it will say, oh, that's 210. Okay, so you don't actually have to do this factorial nonsense. Okay, so anyway, all to say, the pattern that we established earlier was that for the binomial probability, it's the number of arrangements times the probability of success raised to the number of successes times the probability of failure raised to the number of failures, okay? And so if we say we want to get X successes, we have N trials, and the probability of a success is P, then this thing can be written as this. The number of arrangements is N choose X. That's this part right here. N choose X is the number of arrangements. The probability of success is P, and we're gonna need X successes. We raise that to the X power. What's the probability of failure? The probability of failure is 1 minus P, right? So if we said probability of heads is 0.7, the probability of tails is 1 minus 0.7, so that's gonna be 0.3, okay? How many times do we have to get tails, okay? Well, if there's a total of N trials, we need the failure N minus X times. And so this is the binomial probability, okay? And so we can do this ourselves. There is a function on R that will calculate it for us, and we can do dbinom, and the way you enter it is how many successes, X, and how many trials, 4. The probability of success is 0.7, okay? So dbinom 2, 4.7 is 0.2646, which is exactly the probability we got back here. When we did 6 times 0.7 squared times 0.3 squared, that was 0.2646. And we can get that number using R with dbinom for the binomial probability, right? So D is for kind of density. Don't worry about that for now. But we got dbinom 2, 4, 0.7, and you'll go over this a little bit in your lab this week. Okay, why don't we? Let me give you the second quiz answer. Second quiz answer is also E as in elephant. E as in elephant is your second quiz answer today. And we'll take a 5-minute break here. Okay, so we'll take 5 minutes. Second quiz answer is E as in elephant, and we'll take 5 minutes here. Okay, so we left off, and we kind of had this this for the binomial probability. I also gave you your second quiz answer. Second quiz answer was E as in elephant for today. So we have that going for us. Okay, all right, so let's do an example. Okay, so the Golden State Warriors have not had a good season this year. They were the champions, the defending champions for several seasons, but this year was not so good. Steph Curry got injured, but last season, Steph Curry, he had a 92.6% free throw percentage, which is really incredible, actually. So we will say that the probability of making a free throw is 0.296. So that we're going to say probability of success is P equals 0.926. All right, and if you look at his games, you know, some games he takes a lot of free throws, other games he hardly takes any. So we might say in a typical game, he might take something around 5 free throws, okay? So the question here is, what's the probability that he misses one? Okay, so how do we go about answering this, all right? So what we want to do is we want to identify, in order to answer it, so here's our binomial probability, we need to identify these 3 key values. We need to identify what x is, what n is, and what p is. The n, p, and x, these are kind of the values that we need to identify. So n is the number of trials. So n is going to be 5, okay? And p is the probability of success, which is 0.926, and x is how many successes we want, okay? So if we say he's gonna miss 1, then he needs to make 4, okay? So we're gonna have n is 5, p is 0.926, and we wanna know what's the probability that x equals 4, okay? So this is what our answer is gonna be. Binomial problem, n is 5, p is 0.926, x is 4. We can plug in these values. N choose x, so 5 choose 4, 0.926 raised to the 4th, and 1 minus 0.926 raised to the 1, okay? And when you do that calculation, you get something around 0.2720. So if I do 5 choose 4, okay, times, I want 0.926 raised to the 4th, times 1 minus 0.926 raised to the 1. I'm not even going to bother doing that. And if I hit equals, I get 0.7204880, you know, 8345. And again, we can calculate this using R, using D binom. X is 4, N is 5, and P is 0.926. Okay, so these are equivalent ways of getting the same thing. All right, earlier we had this carnival game example, and we said half the spaces are loses and half of them correspond to wins. And our friend played the game 10 times, and he won only 3 times. Okay, if the game is fair, he should have won 5 times out of 10. So how do we distinguish between this and random coincidence, right? An actual phenomenon versus random coincidence. So, so what we want to ask, just managed to reconnect after the break. Repeat question 2. Okay, so sure. Question 2 was E. E as in elephant. Okay. All right. So here, what we're going to ask is, you know, what's the probability that someone would win only 3 times? And I'm going to include or less. Okay. Because we could say, hey, what's the probability that he only wins 3 times out of 10 games? Okay. We could do that. But our friend is willing to accuse the carnival game of cheating because he only won 3 times. He would then certainly accuse the game of cheating if he only won 2 times or 1 time or 0 times, right? So technically, we want to find out what's the probability of that he would get 3 wins or less if he plays the game 10 times. So this is a binomial problem. We've got n equals 10. The probability of winning, if the game is fair in that half of the spaces are lose and half of the spaces are wins, the probability of winning is 0.5, and we want to know x for 0, 1, 2, and 3. Okay, so we can find the binomial probability for when x is 3, x is 2, x is 1, and x is 0. Okay, and I could go through this process of, you know, 10 choose 3, 0.5 to the 3, 1 minus 0.5 to the 7, and things like that. I'm going to just kind of use R to calculate these things. So I do d binom 3 plus d binom 2 with 10.5, d binom 1 with 10 and 0.5, and d binom 0 with 10 and 0.5. And according to this, it says we get something around 17%, which says that even if the game were fair, oh, I didn't finish my sentence, there's still a 17% probability that someone would win only 3 times or less just by random coincidence, okay? Just by random coincidence, this result could have happened 17% of the time, okay? Even if the game is perfectly fair, right? Even if it's a perfectly fair game, just by bad luck or something, you might win only 3 times out of 10, or only win 2 times out of 10. And that's gonna happen around 17% of the time. So to put that in perspective, you know, when I roll the die, what's the probability that it lands on a number 2? That's gonna happen 17% of the time, okay? About that much. So, you know, are they, is the game a scam? I don't know, okay? I would say it could very well have been random coincidence. It doesn't absolve the game. Maybe the game is a scam and we just haven't played enough games to really get to the bottom of this. But right now I would say it's also possible that it's random coincidence, okay? So we'll fully develop this testing apparatus and strategy, and that'll come in chapter 8. But here's just kind of the beginning touches of using probability to start to answer some of these questions here. Okay, just in the interest of time, we're not going to do these, but let's say, but here's some exercises you can do, and these are the answers that you'll get. And so you can do these exercises on your own time as just kind of a little bit of practice here. Okay, and then for the binomial distribution, if we want to know the mean is n times p. Mu is equal to n times p. And then the standard deviation sigma is the square root of n times p times 1 minus p. These are just kind of formulas that I'm not going to try to derive or anything like that. That's reserved for a little bit more of a technical course, but these results are useful to us. So I'll put these in here and just kind of say, like, these are formulas that you use, okay? Okay, I'm going to move on to the normal distribution, okay? So the normal distribution is this, you know, what we call the bell-shaped curve. It's unimodal and symmetric. It's a continuous distribution, okay? And it is tall in the middle, and it is low. It takes, it's close to 0. The curve is close to 0, where we're much higher or lower than the middle, okay? So values near the center show up frequently, okay? Values that are greater than the average or less than the average show up less frequently, okay? And values that are much greater than the average show up very infrequently, almost with 0 probability. Values much lower than average also show up very infrequently. And like all probability distributions, okay, if we take the total area, the total area is 1, okay? And we can get an idea of a certain probability by finding the associated area with kind of the question that we're asking. All right, so the standard normal distribution, called the z-distribution, it has mean equal to 0 and standard deviation equal to 1. This is actually a picture of the standard normal. When the distribution is continuous, the probability of getting any one exact value is 0, okay? Getting an exact value is 0, but we can kind of find the probabilities associated for an area. And so we can ask, what's the probability that z is less than 0, okay? What's the probability that z is less than 0? And so we might write this mathematically using this notation. We can just say, what's the probability that z is less than 0, okay? And the answer is, well, I could draw a line at 0. And the area to the left of this, okay, area to the left of z less than 0 is going to be equal to 0.5. All right, so this area over here is going to be 0.5. All right. Okay, what if I ask this question? What's the probability that z is greater than or equal to 0? So what if I ask, what's the probability that z is greater than or equal to 0? Right. So if the area to the left is 0.5, then the area to the right is also going to be 0.5. Okay. All right, we got a question that says, what do you mean that the probability of getting any one exact value is 0? Okay, so the question is, what is the probability that z ends up exactly at 0? Okay, with infinitely many decimal points, right? So it's kind of like the question, you know, if I pick a handful of sand, what's the probability that the handful of sand is exactly 26.3377864210000000 grams? Exactly that value. And the probability of getting an exact value with infinitely many decimals of precision, the probability of getting that exact value is 0. You can't, the probability of getting one particular value where it matches exactly to infinitely many decimal places, it has a probability of 0. Okay, it's kind of like if you draw a dartboard and you draw a dot. Okay, a dot, 1 point. This is a point, not a circle, not a tiny little circle. Okay, but 1 point, and then somebody else. And you ask somebody to throw a dart or basically pick another point, what's the probability that their point and your point will be exactly the same? And the probability is 0, okay? If you have anything other than a point, like a circle, where it has a little bit of area, then you don't have 0 probability because the areas can overlap. But if you have a point, okay, a single point which has technically no area, it's just a single coordinate or point in space, you know, the probability that of 2 random points being exactly equal to each other is 0. Okay, and the same that any one particular value being equal to another particular value, again, is 0. And I hope that's okay. You basically just have something of that is infinitely thin. Okay. But anyway, I don't want to belabor that point. The probability of being lower than 0 is 1/2, and the total area is 1, so the probability of being above 0 is also 1/2, right? So we can just do 1 minus the probability of being less than 0, 1 minus 0.5, and that's also going to be 0.5. Is that okay? We had the empirical rule. So if you remember the empirical rule, we said, so this was I think back to our second lecture, okay? So this was week 1 on Wednesday. We talked about standard deviation and z-scores. So z-score is the distance from the mean expressed in standard deviations. And that's the z-score. And we said z-scores are between 1 and -1 around 68% of the time. And we can express that using kind of our probability notation and saying the probability that z is between 1 and -1 is around 0.68. And we can do this for z between 2 and -2, and that's going to be around 95%. And z being between 3 and -3 is around 0.997. And so visually, this is what it looks like. And I kind of want to color these in. I'm not able to color it in. using using this. So this is what we have here. Okay, so so what we're saying is that if I take this, where is this not working? There we go. Okay, if I color this, all right, so the total area of this thing, okay, the total area of this, the total area of the curve is equal to 1, okay? The area in the middle, this area, this corresponds to around 68%, okay? This is about, okay? And that goes from z-score equal to -1 to 1. If I go out a little bit, out to here and here, okay, then this area from here to here which goes from z equal to -2 to 2, this is around 95%, okay? And then if I go out all the way to 3 and -3, this gets almost everybody, almost everyone. Sorry, that looks terrible. Use my assisted straight line tool here. Okay, so this is pretty much almost everyone, 99.7. You can see there's only a tiny bit left, okay? And technically it goes off to infinity. The normal distribution goes off to positive infinity and negative infinity. But it just, you know, above 3, above 4, you know, the probability is really, really, really small. It's not 0. It could happen, but the probability is really, really, really small. So we're getting almost 99.7%. I mean, almost 100%, 99.7, pretty low probability, okay? So that's what we've got, the empirical rule there, which we covered way back in chapter 3. We're seeing it again, and it's colored in like this. Let's see, do we have time for this? I think so. Okay, so if we use the empirical rule, and you can just think about this. So think about this, write your answer down, and then in a minute you can throw your answer into the chat. But don't throw it in the chat just in case somebody else is thinking. I don't want them to, their answer to get thrown out. Okay, so using the empirical rule, approximately what proportion has z greater than 1? Okay, so z greater than 1. So I guess in our picture, so I'll save this or something. So this is, again, don't throw it in the chat just yet, but just think about what your answer is. And the question is asking, what is the probability that z is greater than 1? So what we want to know is basically what is this area over here for the probability that z is greater. Okay, so I want to know, okay, z greater than 1. Probability z is greater than, what is the area over here? All right, do you guys think of your answer using the empirical rule? So we know, this is kind of what we know so far. All right, so if you think you know the answer, go ahead and throw it in the chat. All right, okay, yeah. So we got 16%, around 16%. Yeah, exactly, okay. So yes, the answer is around 0.16, right? So we've got, and the reason for that is we've got 68% in the middle, okay? So we know we've got 68% in the middle, and approximately there. And so, which means outside of that, right? So if I've got, this is my terrible picture. Okay, if I've got 0.68 in here, that means out here and out here, it has to add up to 32% because we've got the total area has to add up to 1. And this 32% will be divided equally. And so we'll have around 16% over here and around 16% above. Okay, so we're going to have half of 16% to be less than 1, -1, and about 16% to be greater than 1. We got that. Okay, Louis says 15.85. Yeah, so you can look it up in the table and get something a little bit more precise. Okay, but just using the empirical rule, we get something around 16%. Okay, so what do we do though if we get a question like, what is the proportion that z has less, that z is less than, what proportion has z less than 0.42? So what's the probability that z is less than 0.42? Okay, so our diagram might look something like this. We've got 0 in the standard normal, 0 is in the center, and I'm not all the way out at 1, okay? I'm at 0.42, and I want to know what's the probability that we're less than 0.42, okay? So we can answer this using the z table. So in on CCLE, I've posted this table called Reference Tables Gold. All right, and there's several pages here, but the first one is standard, the normal table. The normal table. Okay, and so what we're going to do is for z being 0.42, we're going to look up the row. Z is 0.4 and the column is 0.02. Okay, so I'm going to come down to here and I'm going to look up the row 0.4, the column 0.02. All right, I think I got this on the slide. So this is kind of a zoomed in thing on the picture. We're going to go to the row 0.4 and the column 0.02 because we've got 0.42. So the intersection of the row 0.4 and the column 0.02 is 0.6628. So that's our answer. What's the probability? What is this area? We know it has to be over 0.5, and the answer is around 0.6628. Okay. You can also get it from the calculator, from R using P norm. You can just say P norm 0.42, and R gives you more precision, 0.662757, okay, which rounds off to 0.6628. Okay. On the exam, kind of all of my answers will be rounded off to 4 decimal places to kind of match what you get from the Z table, okay? But if you want to use R, you can use R, and it'll just carry a little bit more precision here. Okay. So one thing to note is that the table, the Z table and P norm always, 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 always give the area to the left, okay? They always give the area to the left. So if you want the area to the right, you take that number from the table or you take the number from P norm and you subtract that from 1. So if I said, what is the probability that Z is greater than 0.42? Okay. So right now my diagram, let's go ahead. Okay, there we go. So we're at, we have something like this, okay? So we are at 0 and we got 0.42. And we said the area to the left is 0.6628, which means this area over here has to be 1 minus 0.6628. Okay, so we're going to get 0.3372. Okay, because the total area is equal to 1, right? Total area. So that's what we're going to have here. Okay, so we find the area to the left of 0.42, and that's 0.6628. The area to the right of 0.42 is going to be 0.3372. Okay, so so I hope you guys are okay with this notation. Z greater than 0.42 versus Z less than 0.42. That's kind of what we're going with here. Let's see. Do I want to do this right now? I'm going to skip these. Okay. These are some exercises that you guys can try out just to get a little bit of practice of using the Z table. But in the interest of time, I'm going to just kind of skip over these. Okay. So you would look up, you know, row 1.4 and row 1.0 and column 0.04 and things like that. There's also a useful shortcut is that the area to the right of Z is equal to the area to the left of negative Z. So in this picture, we asked, what's the area to the right of 0.42? Area to the right of Z equal to 0.42 is 0.3372. Okay. I could you could imagine taking this and flipping it around, right? And then we would have it's a symmetric diagram. So this would be negative 0.42. And so the area to the right, this area over here, is also going to be 0.3372. Okay, area to the left of Z equal to negative 0.42 is also equal to 0.3372. Okay, and I can verify that by going to the table. I look up Z equal to negative 0.42. I go to this row negative 0.4 and the column 0.2. Okay, and I get 0.3372. All right, so the area to the left of Z equal to negative 0.42 is equal to 0.3372. Area to the right of Z equal to positive 0.42 is the same, because these the normal distribution is symmetric. So you could, you know, visually take this and kind of flip it around. The positive values become negative, and the area to the right becomes the area to the left. All right, we can expand this to generalize the normal distribution. We don't have to be stuck using the standard normal, okay? However, we only have this standard normal table, so what are we supposed to do? Well, if we have another normal distribution, and it's not part of this, it's not the standard normal one, what we do is we standardize these values, okay? So the example I'm using is in the United States, the height of adult men is approximately normal with a mean of 69.5 inches and a standard deviation of 3 inches, okay? So the mean, so this is about 5'9", 5'9.5", something around there, okay? That's gonna be the kind of the average height of adult men in the US, standard deviation of 3 inches, okay? And so the question could be, what proportion of adult men are shorter than 72 inches? So that's shorter than 6 feet tall, okay? So we're gonna ask, what's the probability that height is less than 72. Notice this is a shorthand way of reporting this. Normal, approximately normal with a capital N. Mean, 69.5, that's mu 69.5. Standard deviation, 3, okay? So this is our shorthand way of writing this, and we can just say, what's the probability that Z is less than 72? Okay, so I always recommend drawing a picture first. And really, the only values you need in the picture is what value goes in the middle, the mean, and then you just need to know 72 is, does that go to the right or to the left? 72 is bigger than 69.5. So 72 goes here, and then just from the picture, shorter than 72, we know the answer has to be, it has to be greater than 1/2. Okay, and that's just gonna be kind of a reality check, a common sense check, just to make sure that you're not making some kind of egregious mistake here. Okay, so how do we answer this? Well, proportion of men are shorter than 72 inches. What we're gonna do is we're gonna convert this to a z-score. So the z-score is x minus the mean divided by standard deviation. So how far is 72 above 69.5? Expressed in standard deviations, it's around 0.83 standard deviations above the mean. And so the question of what is the probability that height is less than 72 can be converted to the question, what is the probability that Z is less than 0.83? Okay, and with that, we can go to the table and look up probability that Z is less than 0.83. So I go to the row 0.8, the column 03, and I get 0.7967. So I get probability that Z is less than 0.83 is 0.7967. And that's our answer. Would always tell you if the distribution is close to normal. Yeah, so the problem will say something like height, let's assume height is normally distributed, okay, or something. So, so yes, I will tell you that something follows a normal distribution. Okay, why don't you guys try this? What proportion of adult men in the US are shorter than 71 inches? Okay, so you can go ahead and try that. And I'll give you about a minute to work on this. Okay, and while you guys are working, I will give you your final quiz answer for the day. Final quiz answer today is A as in apple. A as in apple, that's the third quiz answer for today. A as in apple, for your third quiz answer. Okay, so I don't know. I hope you guys try this rather than just sit and wait for me to give you the answer. Okay, did anyone get a z-score? What did you guys get for your z-score? Okay, great. So your z-score is 0.5, exactly. Okay, so our z-score is 0.5, and then, then what is your answer? If your z-score is 0.5, your answer is 0.6915, exactly. Okay, so here I'm going to put z, 0 is there, we get 0.5, and we want to know what is this area to the left of getting less than 71. So we go to the table to look up z equals 0.5, okay? And so we look up 0.50, all right, oops, and we get 0.6915, okay? So we're gonna look up 0.50, and this area, the area is equal to 0.6915. 0.59, 0.69. Okay. So so that's your answer. Yeah, exactly. So your z-score is 0.5. You look that up in the table and you get 0.6915. To use R, can we also use p-norm using 0.5? Yes. So if you want to use R, there's a couple ways you could do this. So you can just do p-norm 0.5 and you get pretty much 0.6915, 0.6914, 625. Okay. I think in your lab you'll learn a little bit more with p-norm. So technically you can do. I hesitate to show you this. p-norm 7169.5, 3. You can put them all in there and you get the same answer there. But you know, on an exam, I might ask, you know, what's the z-score? What's the probability that it's less than 71? You get 0.6915. Okay. I didn't write the answer for this. So here we can say, what's the probability that a randomly chosen adult male has a height between 71 and 72 inches? Okay. All right, so in the interest of time, I'm going to just go very quickly. And I might not even solve this. Well, actually, I think I can solve it very quickly. So, I got 69.5. And basically, the diagram looks something like this, okay? 71 and 72. And what I want to know is what's the area in between? What's going on here? Okay, and so the way it's going to work is this is the area that I want to get. Okay, this is the piece that I want. And what we're going to do is we're going to take the area, everything to the left of 72, and then we're going to do minus. So we're going to do this minus everything to the left of 71. Okay, and then what we'll have left over, if you take everything to the left of 72, and you subtract off everything to the left of 71, you'll be left with the piece that you want, okay? And so I think in our slides, we found the area to the left of 72 to be 0.7967. So this is the area equals 0.7967. So the probability that height is less than 72 is equal to 0.7967. And then here the probability that height is less than 71 is equal to, I think it was 0.6915. So here we got 0.7967, and here was 0.6915, which means the area between 71 and 72, the probability that 71 is, that our height is between 71, and 72 is going to be 0.7967 minus 0.6915. So what is that? 0.1052. Okay, and this is our answer. So this area here, 1052. Okay. All right, got a couple minutes left. Sometimes we need to work backwards, right? So it says here, what size must a hat accommodate if it's to fit 96% of people's heads? All right, so what I want is I want 96%, kind of the middle 96%. So we're gonna get, say the maximum size will be the 98th percentile, and the minimum size will be the 2nd percentile. So this will cover the kind of middle 96% of heads, all right? And so I made up these numbers, but we're gonna say the mean head circumference is 23 inches, and the standard deviation is 0.8 inches. I have no idea, I'm making this up. Okay, so let's try this out. Okay, so we're gonna say head circumference, normal distribution, mean of 23, standard deviation of 0.8. Now, the question is, what is the 98th percentile for head circumferences? Question, do you always assume that the distribution is centered in the middle? Couldn't you technically have 96% be all the way to the left? Technically, yes. I guess just for kind of simplicity, we'll go for the middle. Because if we wanted to do everything to the left, 96% all the way to the left, technically we have to accommodate head circumferences from 0. Because the normal distribution will technically goes to negative infinity, but you can't have a negative head circumference. But we'd have to then go from 0 all the way up to 96%, because this left tail technically goes off to infinity or positive infinity. So you know, to kind of avoid that. But I guess you can make the argument 1% to 97% or something. So here we're going to say, let's just find this 98th percentile. And so the first question is, what is the z-score that's going to give us an area of 0.98? An area of 0.98. Okay, so when we do this, we have to be careful. Okay, we don't want to look up, we don't want to do this. We don't want to go z equals 0.98 and get this number, 0.8365. That's a mistake. Don't do that. Okay, what we have to do is we have to search all of these numbers, and we have to find the number that's closest to 0.98. And so for us, that's going to be this number here. 0.9798 is very close to 0.98, and that corresponds to z equal to 2.05. 2.05. Okay, this is the number we want. 0.9798 corresponds to z equal to 2.05. Okay, and it can be a value smaller or higher. It's not like Price is Right. You can go 0.9803 or something. In this case, this one is only 2 10,000ths away, while this one's 3 10,000ths away, and that's why I chose this one. Okay, but if we had like 0.9801, I would have picked 0.9801. That one's closer. But as far as 0.98 goes, 0.9798, that's the closest value I have. So, so for the 98th percentile, that corresponds to z equals to 2.05. Okay, and so what I do now is I'm going to plug this. We said head circumference is this, and this is the formula for the z-score. We have z equal to 2.05, and we're going to plug that in and solve for x. So z is 2.05. We don't know x. We know our mu is 23. We know our sigma is 0.8. And we solve for x. I multiply both sides by 0.8. I add 23 to both sides. And x is, oh, I guess it didn't got cut off here. It's going to be 24.64. That's going to be our answer. Our answer is 24.64. Okay, we're out of time to do the second percentile. Is there a way to find the z-score using R? Yes. there is a way, and you do Q norm. So there's P norm and Q norm, and if you want Q norm 0 and you type in 0.98, it's going to give us a number very close to 2.05. Here it gives me 2.0537. It's a little bit more precise than what the table says. So if you do Q norm 0.98, you get 2.05, and then you can solve here. The third quiz answer, I gave that earlier, that is A as an apple. A as an apple is our third quiz answer. And that's it. That's it for today. I've given you some homework for chapter 6 for you guys to start working on. And on Wednesday, we will have a review, kind of going over, we'll do some practice problems. So on Wednesday, be ready to do a little bit of work in class. A lot of it will be kind of like I put up a problem on the screen, and I want you guys to answer. I think that'll be most useful for your time. And again, Wednesday's session is optional. So if you don't come on Wednesday, just make sure you come to the final exam, or not final, the midterm exam on Friday. Will our quiz 2 be graded before Wednesday? Let's see. I'll ask the TAs to try to the graders to try to get it turned around as quickly as possible. But I can't make any promises here, okay? But we'll try to get them graded quickly. So we have that. Okay, so we'll see you guys maybe on Wednesday, but if not, definitely on Friday. Come either at 10 a.m. or 10 p.m. On Zoom with your cameras on for that. Okay, thanks guys. We'll see you guys either on Wednesday or Friday.